We start the afternoon session with Professor A.K. Pani from IIT Bombay. So a few words to introduce him. He is one of the collaborators of our dear friend Vasu. And his Pani's interests are in numerical approximations of PDEs. And his expertise includes construction of numerical schemes, efficient schemes, stability, convergent analysis of finite element methods, finite difference schemes, and also orthogonal spline collocation methods for free boundary problems, partial integral differential equations and coupled equations in oil reservoir studies and many other problems, evolutionary variational inequalities, including that. So his focus is in computational mathematics and to develop efficient and accurate solutions to real world problems with a strong theoretical flavor. So I'm happy he is joining us today. So I invite him to give the first talk on fractional time evolution equations in this afternoon session. Now over to you, Professor Pani.
Okay, thank you, Maithili, for nice introduction. At the outset, I would like to thank Venki and Pavan for arranging such a meeting and inviting me to say something about Vasu. So let me start with my interaction with Vasu. I have a very long interaction with Vasu. It started in 1986. When I was visiting TIFR Bangalore in ISC campus, there was an Indo-French workshop. I think we met there, and subsequently we became good friends. And our common friend Vidar Thome, he also visited us and TIFR Bangalore campus. And let me tell you my interaction with him in various ways. So when Vidar Thome came to TIFR Bangalore campus, he visited Mumbai, IIT Bombay, and on his way he wanted to talk to TIFR Bombay people regarding applied mathematics, but I think he was disappointed. So then Vasu and me, we thought locally we'll start organizing some events to popularize applied mathematics one way or other. And it was a good thing that Neela Nataraj joined IIT Bombay. And then we started doing some 3 weeks long workshop every year without even support from NBHM or other agencies. We just bank on the registration fee and some money which we had RDF, we spent it. And in one occasion, the first occasion when we didn't have money, Vasu paid his own ticket, came here, and he was there for the events. And this is how Vasu is. Subsequently, other events we organized. Many of our senior TIFR Bangalore friend helped us, but particularly Vasu was always there. Then we started thinking of NPD, National Program on Differential Equation. We worked for 5 years with DST, then subsequently got that program. It ran for 5 years. But Vasu has certain objectives. He believed, and that also, I think I also believed it, and that becomes the theme of the National Program on Differential Equation. The theory and computation goes side by side. So that was one of the theme of the NPD program. And NPD program we ran for 5 years. And when I go and see people in different places, the students are coming naturally to work on differential equation and numerical analysis. Of course, it will be a better tribute to Basu if we can revive the same program once more, so as to develop awareness, greater awareness in applied mathematics. Well, this is, I can't believe that Basu is not with us now. So, but it is, I think what I say, he is always there in your mind. So with this, let me start my talk. I say I will talk about fractional in time, evolution equation, theoretical and computational issues. So this work is in collaboration with my friend Samir Kara from Muscat, Kashem Mustafa from King Fahd University of Petroleum and Minerals, and also my friend from Chester University, they win one. And another friend from Hong Kong Polytechnic University, Z Zhao. We are still working on some aspect of this fractional evolution equation. So I will start quickly some problem formulation and talk about the fractional calculus. I will talk about a simple differential equation which will pave a way to understand the abstract evolution equation, a fractional order evolution equation, let's call it. And in the process, I will talk about the representation of solution and what were the theory in heat equation can be used there. That is one of our objectives. Then we talk about regularity and some important tools. And then I will talk about what is our contribution, what was lacking there and what we did. Well, let me go straight to the fractional, time fractional subdiffusion equation it is called. I will call why it is called subdiffusion. So let us take omega is in RD. In particular, I have taken R2, but many things which I'm going to do, it is going to be in RD. Omega is a bounded domain. Of course, we can assume it is a convex polygonal polyhedron. Then your time variation is from 0 to capital T, and U is a function of x and t. U prime, when you say U prime, this is going to be partial derivative of U with respect to time. Minus, there is a symbol called D, 1 minus alpha acting on Laplacian U. For simplicity, I have taken this, but I will tell how you can generalize this minus Laplacian to any other second order elliptic problem. Of course, a Fadgen elliptic problem. And the forcing function is F, is a function of x and t. We have two boundary, one boundary condition is U on the space-time cylinder. You take on the lateral part of this is U taken to be 0, but you can take also Neumann boundary condition, Robinson boundary condition, and so on, so forth, and take U t is equal to 0 at initial condition. You take U to be given function U0. So what is that symbol D1 minus alpha? We will describe in the subsequent slides. It is called Riemann-Liouville time fractional derivative order 1 minus alpha. When alpha lying between 0 and 1, and when alpha tends to 1, it is called the standard diffusion diffusion equation, because if it is alpha tends to 1, this is going to be u prime minus Laplacian u. But we are interested in when alpha is lying between 0 and a half, and it is called slow diffusion or subdiffusion problems. Okay, so before I define this derivative, let me talk about fractional order integration. So you start with a symbol I to the power 0, f of t is your f of t, and I1 f of t is, or simply write I f of t, I acting on f of t, it is the integral of ft 0 to t ft dt or fs ds. So likewise, you define what is called I to the power n f of t. N is an integer, positive integer. This is 1 by n minus 1 factorial. Integration 0 to t, t minus s to the power n minus 1 f of s ds. So let us ask a natural question. If alpha is going to be greater than or equal to 0, any real number, so can you generalize this? Yes, it is possible, because the factorial function is your gamma function, so you know this generalization. And 0 to t minus s to the power alpha minus 1 you can write down, and wherever it is, it is going to be meaningful, it is finite, they are going to give I to the power alpha f of t. Yes, it can be generalized. So this is known as Riemann-Liouville fractional integral of order alpha. The good thing about that is equal to 0, this guy is going to be, when take it 0 plus I of f, I alpha of f of t, it's going to be I alpha of 0. So let us look at some of the properties which will be fundamental in later developments. So this kernel function here, you just write down, we are now more or less interested in alpha is lying between 0 and 1. So this kernel function is a singular kernel function, so let us call it phi alpha. So therefore, I alpha f of t can be written as a convolution of phi alpha convolute with f of t. So using this convolution, you know that convolution operators are commutative. So you can write down the commutative property of this integral operator I alpha. And also it is satisfied some semi-group property. It has the same properties as the convolution phi alpha, phi beta, phi alpha plus beta. So this is going to be I alpha plus beta. Well, so what happens if t to the power gamma, something you walk I alpha and t to the power gamma, it behaves like a similar way on integrals with this pollution term. So this is going to be 2 to the power gamma plus alpha. Of course, gamma is going to be greater than -1. Well, the best part of this thing is it is written as a convolution. You can talk about the Laplace transformation. And Laplace transformation is fundamentally very much used in these areas of mathematics. So let us talk about how the Laplace transform behaves. The Laplace transform of I alpha f of t, it is going to give you the Laplace transform of phi alpha, the multiplication with Laplace transform of f of t. But Laplace transform of this singular kernel, this guy behaves to the power s minus alpha in the Laplace transform variable, and then this is the Laplace transform of f of t. And since it behaves like in this way, and it is very popular to use Laplace transform in the direction of time. Well, how do I define the integrals? derivatives, you just write down, just differentiate this guy. D acting on I1 minus alpha, you call it d alpha of t, that is called Riemann-Liouville fractional order derivative when alpha lies between 0 and 1. If alpha is between n and n plus 1, similarly you can define it. It's the same definition. But let me go back to 1695 when Leibniz gave the symbol what you are using for differentiation. He was talking about dn x by dt, nth derivative of. Then L'Hopital sent a letter to him in 1695. What happens when n is equal to half? This is popular example which people give in fractional or differential equation. So Leibniz replied, this is an apparent paradox from which one day useful consequences will be drawn. And perhaps that time has come. Last 10 to 15 years, a lot of people are working on fractional order differential equation, space fractional, time fractional, and so on and so forth. And there are a lot of work is going on. Okay, so if I compare with the standard derivative, it is local in character because you are finding derivative at certain points. So there is a neighborhood, we talked about that one and things like that. So this is local in character. But fractional differentiation is not local because this integral term comes from 0 to t. So it is non-local in character. That is why it is very much used in the modeling of materials, elasticity, viscoelastic material, and so on and so forth, where the process will have some memory. It is very much used in application, even in 50, 60 years back, people have been using it. So what are the properties of Riemann-Liouville fractional derivative? Well, this is the left inverse of I alpha, but it is not the right inverse. But its action on t to the power gamma, it behaves like the standard derivative gamma minus alpha. But when you have a constant function, or you take a 1, the fractional order derivative, Riemann-Liouville fractional order derivative, when it acts on 1, it behaves like t to the power minus alpha. That's a, well, it is a surprise, but that comes from the behavior of these integrals. But when f0 is not equal to 0, these guys are behaving the derivative. The fractional order derivative will behave like t to the power minus alpha as t tends to 0. So it is the major difference between heat equation, you will see later on, the standard derivative or heat equation and this, because there is a singularity of the fractional derivative you take, there is a singularity of t to the power minus alpha. And this is the problem in dealing with the fractional order derivatives. But surprisingly, if you take d alpha, acting on t alpha minus 1, it becomes 0. So you can see quickly that it behaves, et is going to exponential t. It is going exponentially, but the fractional order Riemann-Liouville derivative due to the power half, acting on et, there will be a singularity of t to the power minus half. So it behaves of this kind. It goes slowly. It behaves like this. Okay. But Michael Caputo was interested in theory of elasticity and seismic waves or viscoelastic materials. So he was interested in, like, the standard derivative, I should have derivative which is going to act on a constant function gives you 0. So what he did, he just flipped the definition. Riemann fractional order integral of 1 minus alpha, he just write down the capital derivative d alpha of f of t is I, it will be 1 minus alpha, let us call it alpha lies between 0 and 1. This is n is equal to 1. 1 minus alpha d of ft. D means standard derivative. So if you see compared to this definition, this is other way around. And they are not commutative, so these definitions are not same. But they behaves in a similar manner. I will tell you what is the major difference. Okay. So by doing so, he get the capital derivative acting on 1 is going to be 0. And he can write down if as certain, so there is a chart. Oh, physical interpretation, somebody asked, it is non-local in character. So we can say things only about the non-local in character. So physical interpretation is when there is a something with memory, it will represent that. Okay. So f is differentiable sometime, then you can write down I to the power n ft in this form. And if you walk to the derivative there, fractional order derivative, it is going to give you the Caputo derivative. Fractional order Riemann Liouville derivative, then it is going to Caputo derivative. So for an example, when n is equal to 1 and alpha lies between 0 and 1, the only difference between Caputo derivative and Riemann derivative is d alpha acting on f of t minus f of 0. Okay, so it is the difference. All right, so now you can see 3 of them. Caputo derivative, you can see that there is no singularity in this case. This is your ET, and this is going to be your the Riemann Liouville derivative acting on d to the power half e acting on e, and this one, the last one, is going to be your Caputo derivative of ET. So there is no singularity, it has removed. So I will start with a simple differential equation involving Caputo derivative, because Caputo derivative and Riemann derivative have some relation, so one can exploit what if you one get one, the other one can find out. So why I started with this simpler definition, this is called Caputo derivative of alpha, fractional order ordinary differential equation plus lambda time u plus f of t. I want to study this because when I go for abstract revolution equation, fractional order evolution equation, then using Fourier representation for each lambda, each eigenvalue, I can write down similar equation. There will be infinite number of similar equations. So it is better to study one of them. That will help. So how do you study this? The standard way to apply the Laplace transform. So you apply Laplace transform. Laplace transform is alpha, so it will behave in this way. And you can write down u, the Laplace transform or u0 divided by s plus lambda time s alpha minus 1. F, let us think f is equal to 0. Then you have to take inverse Laplace transform. So if you take inverse Laplace transform and u0 is equal to 1, you let us think, you get some what is called Mittag-Lefferal function. E alpha, which I will describe in next slide, E alpha minus lambda t to the power alpha. The argument is minus lambda t to the power alpha. So using this representation, I can write down is in solution for this problem. So simply you can write down the solution for this problem using this Mittag-Leffler function. So what is Mittag-Leffler function? That is behaves like z to the power k by gamma alpha k plus 1. Alpha is greater than 0. Z is going to be a complex number. Well, we can talk about complex number, analyticity, and all other things. Anyway, you are not going towards that. So when alpha is equal to 1, this is your standard exponential function. And alpha lies between 0 and 1. It is represented by Mittag-Leffler function of this kind. And this is the solution when f is equal to 0. So what is the behavior of this Mittag-Leffler function? So as t tends to 0, this Mittag-Leffler function will behave like t to the power alpha. So that means its derivative will have a singularity there. But at infinity, how does it happen? At infinity, it is algebraical decay. It's decaying algebraically. There is another question. Yeah. There is a question, which derivative is physical more relevant? Well, both of them I should say, but Caputo is more relevant because in viscoelastic materials, when you model it, or poroelasticity material, something you model it, you get a similar type of derivative in terms of the integrals. So both are useful in application. So u prime t is going to behave like t to the power alpha minus 1. So that is have a singularity, and algebraically is decay like t to the power minus alpha. So it has a behavior like a wave equation because it's algebraically decay. Some kind of, it lies in between there. Okay, but this is exponentially decay. This is algebraically decay. The decay estimate I had given. Now let us take this differential equation. I can write down one in terms of other. Cleverly, what I do, u0 is equal to 1. I have taken. Otherwise, you can see the difference. You can write down equivalently in other form. And of course, for the second one, you can write down same way the solution. So it doesn't matter. It doesn't matter. If you do one, you can other can be done. But if there will be a non-homogeneous term, then there is a difference. There will be some difference because there will be some singularity. When you go from here to here, there are some interplay we have to do. And it has some properties. The Liouville integral operator, Riemann-Liouville integral operator, it is positivity property is there as long alpha lying between 0 and 1. But if it is going to be 1, this is going to be greater than equal to 0. You cannot get this. So sometimes people avoid to use this one because they want to get some estimate which is valid uniformly for every alpha, even alpha going to 1. But second one, unfortunately, C alpha will blow up when alpha goes to 1. So if you are looking for some uniform estimate in for your differential equation, which is valid uniformly for all alpha, alpha going to 1 plus, then you should not use this. Okay. So this was very nicely proven by MacLean. William McLean's, and this is very well written paper. So let us go for abstract evolutionary equation, because the equation which you have written earlier, here minus Laplacian u, AU, if you write down minus Laplacian u, that is the earlier you have written down. So in order to write in general form, abstract form, seemingly different problems you can put under one umbrella. So if A is a linear operator with a dense domain, and we'll assume that A is a self-adjoint and positive definite later on, having the inverse being a compact linear operator, then instead of minus Laplacian u in a bounded domain, you can replace by any uniformly elliptic second order, y second order, fourth order also uniformly elliptic operator which you are self-adjoint. You can replace by that. So in this case, what is your H is going to be L2, domain of A is going to be H2 intersection H01. H2 means along with his second derivative, they are all square integrable. H01 means the derivative is square integrable along with the function, and it vanishes on the boundary, if you are not familiar with this notation. Okay, so we will work with this abstract evolution equation, because seemingly different problems can be put under one umbrella. So theoretical study, people, what they do, they just integrate it. After integration, you will get some Volterra integral equation of second kind. And Volterra integral equation of second kind, of course, there is singular kernel, but they are well behaved. So a lot of theory is developed based on this, theoretical study based on this. Yeah, can you explain the term memory that the material possesses? Well, if I get time at the end of the lecture, I will tell you. I will be running out of time. Or you can ask that question later on to me. Okay. So this is the way the standard theoretical study people do. Well, since L is self-adjoint and positive, and its inverse is going to be a compact, so it will have a complete orthonormal eigensystem. So A psi m is going to lambda m psi m, and all these psi functions are going to be orthogonal. Let us assume that. And for this problem, eigenvalues are positive because it is going to be positive definite operator. So all going to be positive, and you have a relation like this lambda n, as n tends to infinity, which possesses the behavior of unbounded operator. So let us look at the Fourier representation of ut in terms of this eigenfunction expansion. So this is summation of umt of psi m, where psi m is already known. So what is umt? This is called the Fourier. This is called the Fourier coefficient. Okay, this is L2 inner product with ut and psi m, or instead of L2 inner product, you can say inner product defined on H. And if F is known, so that this representation is known, U is known, U naught is known, this representation is known. So I am going to plug it in the main equation. So when you plug it in the main equation and use the orthogonality property, then you will get infinite number of similar equations like which we have discussed earlier. Um prime plus lambda m d1 minus alpha um fmt. And you have, using Laplace transform, you have already got a representation of the solution. So you can write it down. So thereby you can get a solution operator. ET. You just plugging them together. How you do plug this together? In this place, you write down UMT. So UMT, if you write down in this place, we are going to get an expression of the script T, T acting on V. V is the initial condition if you think of that way. So you can write down in this form. So using this representation, you will write down the solution. The way you do using semi-group theory, the way you have the representation of the solution, here using the not semi-group property, it doesn't have a semi-group property, but it has all the required properties. So let us call it a solution operator. So it has the similar representation. So surprisingly that it is going to be bounded is positive and non-negative and bounded by 1. And this bounded by 1, using Parseval's identity, you can prove the stability. And of course, when F is non-homogeneous, you can get this estimate easily. For finite element analysis or any other finite difference analysis or finite volume analysis or whatever way, or spectral analysis, you need a certain regularity of solution. And the regularity which is you can prove. So for that, I am going to define some space H dot R through this eigenfunctions. So H dot R is written in terms of eigenfunctions, lambda m to the power R, and you have an induced norm you can find out in terms of this. When V is equal to U and take to the power half, this is going to be induced norm. Induced norm is defined through this. But what relation it has with these standard Sobolev spaces? So standard Sobolev spaces of order S to the power R, S dot R is going to be V, all elements be in HR, such that Laplacian Laplacian to the power J V is going to vanish in the bound. And J is equal to R by 2. Well, if you are not familiar with this, you don't worry about that. What I am trying to tell, in finite element analysis, you will come across some spaces H dot 2 plus delta for getting some convergence, where your initial function not only it will be 0 on the boundary, but also Laplacian of that initial function should be 0 on the boundary. But while I am doing the computation, you don't use that. That's the, so that means while doing the computation, the initial conditions are not imposed this condition, which you give the required smoothness there in this. So there are two things we have to worry about. When you do actual computation, you don't pose any of this thing. So therefore, can you develop some theory which will say with the U, the initial condition is in L2, you can prove some error estimate. Of course, in heat equation, you have something called smoothing property. And in this case also, there is some smoothing property, and you can exploit this. So you can have a representation. I'm just, I don't have much time, so I am going. So if you see this, then you see this is the solution. H to the power R plus mu. If you take an initial condition is U naught, you get a factor T to the power mu by 2, and R is equal to, you can take it 0. So R is equal to 0 if you take, that means U naught is equal to for any mu. So it has unlimited smoothing property for heat equation, linear heat equation. But compared to that, let us look at what happens to the smoothing property, the fractional diffusion problem. But unfortunately, it has limited smoothing property. That means if you take R is equal to 0, mu can go up to 2, not more than that. That means mu is equal to 2, R is equal to 0. That is going to be H2 space. Solution is in H2 space. Will tell you T to the power minus alpha mu is equal to 2. So T to the power alpha U0 is going to be near 2. That is the best you can show. Do that. So if you compare to this thing, it has limited smoothing property, but unlimited smoothing property for the linear heat equation. Well, what you do, you standard weak formulation, you take it and pose, you take a finite dimensional subspace of this. What analysis I am going to give, it is not limited to finite element method. You can apply finite difference method, finite volume element method, spectral method, any other method you can apply. That is the beauty of the energy argument, which I am going to talk about. So you take a finite dimensional subspace, this is piecewise linear elements you are take. So in L2 norm, the best rate of convergence is going to be h to the power 2. H is the discretizing parameter. So pose the problem in the finite dimensional setting. So here two main objectives we are going to achieve. Derive error estimates which are optimal, not only with respect to the approximation property, but also with respect to the solution regularity expressed through the data on the problem. Your data means your U0 and F. But earlier, all analyses they are using Laplace transformation technique, but while doing finite element computation, they use energy type of argument. That weak formulation they use. So the energy argument which you are trying to use it here, it is going to open up even for time dependent problems. Okay. So what is the problem? I will just tell the problem and then I will stop it. What is the problem? The problem here, you want to get some kind of a smoothing property. That means you have to push some type of a weight like T to the power M. Okay. But we are for fractional order, there is a difficulty pushing T. So if you take fractional order derivative of two functions f and z, and if you apply Leibniz function, j is going to be j is equal to 0 to infinity, it is going to give you. I mean, you have this, but if one of them is going to be t, and this is your standard derivative, then there will be a truncation. So you exploit this idea, and using this, you have to push t inside this fractional order. I have written b alpha for that d1 minus alpha. You have to push inside this. And that is exactly the contribution of the work. And the rest of this, you can manage. As in the heat equations, you can manage. But yes, non-smooth solution, forget about f is equal to 0. Let us take mu is equal to 2. So this is going to be ch square in L2 norm, t to the power minus t to the power minus alpha u0 in L2 norm. Oh, there are some improvement. You have removed the logarithmic term, which as earlier people have developed it using the other kind of analysis. Okay, so I will stop it here. We have written few papers. Sorry, I have not given the reference to the paper, but I think I have given it here. The objective when I was talking about, yes, 2017. That then after that we have written few more papers. So now, if you look at it, Vidar Thomas' book, The Galerkin Finite Element Method for Parabolic Problem, that is the key book. So people are trying to understand how far the results from parabolic PD can be extended to that, and a lot of people are working on, and they are getting good problems, good interesting results. So this is a key reference to these studies. Okay. Thank you very much.
Yeah, thank you, Professor Pani.